So, hello everyone. This is your course instructor, Khushwant Fatnani. Let us start off with the next session of the chapter Properties of Matter, that is properties of solids and liquids. So, we'll begin this class with the next topic after velocity of efflux, and we'll take up that topic. It is surface tension, right? So we'll see what all topics are we going to cover after this in this chapter, and one by one we'll take up numerical solving, right? All right, so let's begin. So we are seeing the chapter, right? Properties of solids and liquids. And now let us see in today's class the concept of surface tension. Let us see the concept of surface energy. So we are actually revising, right? This is a revision class. So we'll quickly see the concepts and practice as many questions as we can, right? So surface tension, surface energy. We are going to see the concept of angle of contact, angle of contact. We are going to understand what is excess pressure, a quick look into it. But we will make sure that we understand all of this very well before we practice the questions in detail, right? So excess pressure and capillary rise or capillarity, right? So let's begin, class. Let's begin. So first, let's take surface tension. I hope this concept is known to all of you, that surface tension is basically a very special kind of force acting per unit area of any liquid surface. So let's say I have a liquid which is filled in a vessel, which is filled in a vessel, right? Let's say we have some liquid which is filled in a vessel. So here is the liquid. Let's fill out, let's fill in some liquid in it, okay? Now, the concept is that surface tension is actually a property of any liquid, because of which it is the property of any liquid because of which its surface behaves as a stretched membrane, a stretched membrane. So the point is, as you all must have noticed this in your normal experiences, that let's say when I keep a very flat thin blade, right, on the surface of liquid, it starts floating. It starts floating on that surface, right? Now, what is that force which makes this, what is that energy, what is that magic which makes this blade float on the surface of a liquid? So that magic, that energy, that force, whatever you call it, that reason is surface tension. That reason is surface tension. So you define surface tension is the force which is acting on the surface by the molecules, right, or by the water molecules per unit length, right? Force per unit length. So you can define its unit as Newton per meter, right? Its unit as Newton per meter. And we know its dimensions of force are mlt minus 2. So we'll write mlt minus 2. Dimension of length is L. So the dimension of surface tension, let's say I'm denoting surface tension by S, dimension of surface tension becomes mp minus 2. mp minus 2, right? Now, this surface tension is because of a very special property called as surface energy, right? So surface tension is in existence because of a property called surface energy, and you can also call it vice versa. So let's see how. So surface energy, okay? Surface energy. By name, it's very clear. By name, it sounds very clear. The energy with the surface molecules, the energy which is with the surface molecules. So let's say I have these molecules at the surface of the liquid, at the surface of the liquid. What is the difference between two molecules, which out of which one is here inside the liquid, while the other is here at the face of the liquid? See, when for the first time, right, years ago, when I read this concept, right, I was so much enthused by understanding, oh, this is also something which can make or which can build the grounds for surface tension. Wow. So this was the energy, this was the enthusiasm which was filled in me for the first time when I understood about the concept of surface energy. See here, okay? It's a very nice concept. So let's see this. So supposingly, we have, we are talking about different molecules, okay? Let's say this water has different molecules. Let's say this is water, okay? And these are the surface molecules. These are the surface molecules. Assume they are very similar to each other, right? Now let us take molecules below them. So this is one side view, okay? Let's say of the vessel, and you're being able to see the molecules. The molecules may not be so large in size, but then I'm taking them large so that you all can have a good view. Okay, and let's say I take a molecule over here. It also has molecules around it, all around it. Please make this diagram, class, in your copies. Let's see now. Have a look. So, surface energy, right? Surface energy is basically, in essence, the potential energy of the molecules, potential energy of the molecules of the surface film of the liquid by the virtue of its position. I'm repeating, surface energy is the potential energy of the molecules, is the potential energy of the molecules, right? of the surface film of the liquid by the virtue of their position. Seems to be challenging when you read it for the first time, but it becomes easy when you know what is potential energy. So, would anyone like to tell me, Karuna, would you like to tell me what is potential energy? So let's say if we understand this concept of potential energy, no, then the concept of surface energy of the molecules will be super clear to us. That is why I'm asking, what is potential energy? Yes.
So,
Just be a little closer to your mic. Yes.
so I don't know it properly.
Still, just by your vague guesses, anything that you know, you need not be very precise, very correct, or very proper. Go ahead.
Any energy which is given to an object
Yes.
initially.
By the virtue of its position. By the virtue of its position. So energy by the virtue of the position, energy by the virtue of its position is called as, yes, is called as potential energy. Okay.
Potential
Yeah,
energy.
we'll take an example of it. Let's say we have a mountain. Okay. Let's say we have a mountain. Now, from the top of this mountain, let's say this is the mountain. Like, let's say some rocks are there. Okay. Now, from the top of these rocks, there is water flowing. There is water flowing. Let's say it's a waterfall, right? Let's say it's a waterfall. Now, what do we know about the concept of a waterfall? That over here, when the water is there, it might not have a very large velocity. It might not have a very large velocity, but as it comes down, its velocity increases. Its velocity increases. Try recalling from my previous classes, Karuna. Whenever in, in case of gravitation, whenever we used to move an object away from the earth, we used to give the same example. There is an object, let's say this is earth, there is an object here, right? We took this object to some other position. It had velocity v here, v1 here, and velocity v2 here. Then there used to be a change in v1 and v2. At the cost of what? What two things did we use to conserve together? K and
Uh,
K and
Potential energy.
U, right? That is kinetic and potential energy. Why did we use to conserve them? Try recalling. I've always said this.
So mechanical energy is conserved.
Why? Why? The reason I made all of you write the note also 2 or 3 times. Why do we conserve mechanical energy? What was happening there? What kind of force was acting? Whenever conservative force acts on a body, then energy is conserved.
Conserved.
Now, do you recall? Huh?
Yes, sir.
Whenever,
Yes, sir.
whenever conservative force acts on a body, whenever conservative force acts on the body, right? And more importantly, at that time, you should know that the mechanical energy, ME, mechanical energy is conserved, is conserved. So know this thing, right? Let's say I ask you, right? Let's say this is the floor, okay? Karuna, I ask you that pick up a ball from the floor, right? And bring it to height h and bring it to height h, right? So let's say you took the ball, right? And you brought it to height h from the ground, right? Tell me one thing, Karuna. By doing this, now if you leave the ball and you allow it to come down, what will happen? It will have some velocity when it comes down, right? Right?
Yes, sir.
How did that
Yes.
velocity come with the ball? Come to the ball because of
Gravity.
Because of gravity, absolutely correct. But what was the form of energy when it was here, which got converted into kinetic when it came down?
Potential energy converted to kinetic.
Why did that potential energy come in the ball? That is the question. Why did this potential energy come in the ball as you lifted the ball from the ground? That is my question. I want to know the source of potential energy. See, I'll ask you once again. I'm saying, so let's say, right, let's say we have this is you, right? I asked you to pick up a ball from the ground. To pick up a ball from the ground. You did that. You took a ball, right? And you brought it to your hand. Let's say you're holding a ball now. Let's say over here. Okay. So you're holding a ball this way. Now tell me, Karuna, when you're holding the ball in the air and when it was initially on the ground, let's call the positions as cases as 1 and 2. Cases as 1 and 2. Tell me, Karuna, let's say if ground is the reference, let's say if ground is the reference, right? And if the potential energy is 0 on the ground level, then did this ball have any energy at the ground?
No, sir.
But now when you have lifted up to a height h, it has some potential energy? Yes or no?
Yes, sir.
Let's say if the mass of the ball is m, right, and the height to which it has been lifted from the ground is h. What is that potential energy in the ball?
MGH.
mgh. See, you know about it. Now tell me, Karuna, where did this energy come from in the ball? How did it enter into this ball? Did you see it entering the
From
ball?
no, sir.
So from where did it come? Try thinking about it.
It's mechanical work.
Yes. So as you were lifting this ball, you were doing work on the ball. You were doing work on the ball. Now this work done turned into potential energy of the ball. Turned into potential energy of the ball. But it is very important to understand this, that this work has been done against gravity. Where is the gravity acting, by the way? From top to bottom or bottom to top?
From top to bottom.
G is acting in the downward direction. Whereas what is the direction of movement of the ball when you're lifting it?
Upward.
Upwards. So gravity is acting downwards. Mark this, okay? This is very important. Gravity is acting downwards, whereas you are lifting the ball. You are lifting the ball
Upward.
upwards.
Upward.
So this is the concept. This is the funda that you have to understand. What? That whenever, so this concept is against gravity. Okay. Here you have against gravity. So the concept is that whenever work is done on a body against a conservative
Gravity.
force, against a conservative force, whenever work is done on a body against a conservative force, some, or you can write, this work gets stored in the body, gets stored in the body in form of, yeah, in the form of potential energy. Potential energy. Whenever work is done on a body against a conservative force, This work gets stored in the body in the form of potential energy. So the point is, this potential energy is not coming from anywhere. It is being supplied by you. This potential energy, which is present in the ball when it is at this height, it is not coming from any other sources. You are the one to give that energy to the ball as you're lifting the ball from the ground to a height h, right? And how did it enter the ball? It enters because of this principle. It enters because of this principle. In fact, whenever in physics, in the chapter work, power, energy, when we introduce this concept of potential energy, first, before that, we introduce the concept of conservative force. We say that only when there is a conservative force can we talk about potential energy. What did I say? I'll repeat. Only when, only when there is a conservative force, only when there is a conservative force can you talk about potential energy. So potential energy has no existence if there is no conservative force. If there is no conservative force, then no potential energy. If yes conservative force, then yes potential energy. Is the point clear?
Yes, sir.
So this is the funda, this is the concept, this is the working, that whenever there is a conservative force acting and you do work against that conservative force, you are actually supplying energy to that, or energy to that body, which is getting stored as potential energy in the body, right? So have a look here. What happens? Those molecules here, which are here at the bottom, they are being acted upon by force from all directions, right? They are being acted upon by force from all directions, correct? Correct.
Yes, sir.
Whereas what about the molecules which are over here? They are just being acted upon by force from the bottom. Let's say we are talking about cohesive forces. Let's say we are talking about cohesive forces. What are cohesive forces? Cohesive forces are attractive forces between molecules of same type. Attractive forces between similar molecules, like water molecules attracting another water molecule. So I will say they have a cohesive force between them. Co-word means same. Co-word means same, right? Or together. So cohesive forces, cohesive force is basically the attractive force between similar molecules, similar molecules. So what is happening whenever a molecule which is at the bottom in the liquid, that is being acted upon by force from its neighboring molecules in all directions. Whereas those particles which are just at the top are just being acted upon by force from the particles which are below it. The particles which are below it. So see here, there is a magic involved here. See here, here for a particle which is on the base here, right? Net force is 0, right? Whereas a particle which is over here has actually overcome these three forces. See here, 1, 2, and 3. Right or wrong? Karuna, tell me.
Yes, sir.
Anukriti, tell me. Is this concept clear? What I'm saying? A particle which is present on the surface has actually overcome these forces. See, the forces of attraction. Let's say this is the particle, right? So this one, let's say this was the particle which has, and this space was empty. So let's say this particle managed to make sure that it will go here on the top, this will go here on the top, right? So as this water molecules travels over here and fills up this space, what has it done in essence? It has overcome the attractive forces by the other neighboring molecules, and now is being just acted upon by an unbalanced force, which is just by this layer of molecules which is below, layer of molecules which is just below this molecule, right? Which is below this molecule. So this particular topmost layer is being acted upon by attractive forces by molecules just below them, molecules just below them. A layer whereas a particle which is present over here in the bottom is being acted upon force from all the sides. So what has this particle done? This particle in reaching here, in order to reach here, in order to write this down, in order to reach the surface, reach surface, this molecule has overcome, this molecule has overcome the other attractive forces at bottom, which were acting upon it in the bottom. Is my point clear, Anukriti?
Yes, sir.
Mahila, is my point clear to you? What I am saying, that as the molecule is moving up, here the molecule was being acted upon, let's say, by three kinds of forces. I'll give you a very simple example. See, let's say this molecule was acted upon by force F1, by force F2, by force F3, and F4, right? So four types of forces were acting on one single molecule, this one, right? But what happens when it is at the top? Only F3 is acting on it. Only the force by a molecule is acting in the downward direction. There is no more force, or maybe you can say this also. Let's say this particle also attracts, but still, but let's say these are also interacting with each other. So let's say we have forces of attraction between them also, but still there is no layer over here, right? There is no layer over here. So still there are less forces. There is no molecule at the top of that surface, correct? So you have the concept saying that unbalanced forces, I'll repeat, unbalanced forces are now acting on the molecule as it is on the topmost layer, and on in the process of, and in the process of reaching from bottom to the surface, in the process of reaching from bottom to the surface, this molecule has overcome this extra force which was acting when it was below. The molecule has overcome the extra force which was acting when it was below. That force is no longer acting on the molecule. That force is no longer acting on the molecule, right? Clear? Mahila, are you clear with this concept?
Yes, sir.
Now, the way in case of gravity, when we were doing some work against the force and that work was getting stored as potential energy on a similar plane as this molecule which was initially downwards and then it came upwards against the attractive forces which were being acted upon by its neighboring molecules, and it reached the topmost surface. So this amount of work which was done by this molecule, that work gets stored in this molecule in the form of that work. So this work, so therefore this work done is stored in the form of potential energy of molecules, potential energy of molecules at surface. I repeat, the work done against the attractive forces, right? Against the attractive forces to come on the topmost layer, that work is getting stored in these molecules in the form of potential energy of the molecules. And this potential energy is called as surface energy, is called as surface energy, right? My point is clear. Is my point clear, Mahila? Are you able to interpret this properly?
Yes, sir.
So surface energy is, this is how we define surface energy. Surface, okay. So this is how we define surface energy. That surface energy is nothing but potential energy of the molecules at the surface. What is it? It is the potential energy of the molecules at the surface. And how did it enter into these molecules? As these molecules were doing some work against the attractive forces, and as they reached the topmost layer, they possess this work done in the form of potential energy. Right? Clear? Karuna, is the concept of potential energy, is the concept of surface energy now clear to you?
Yes, sir.
Sure?
Yes, sir.
So any point of time later, if I ask you that what is potential energy, then you must not say that, sir, I don't know. Okay. So you need to revise this.
Yes, sir.
Right. Please make sure, class, that you will revise all the lectures. If you don't do, you're actually losing out on the knowledge that we are gaining, right? So please make a habit of giving a recap to yourself after every class. Okay. Yeah, good. Good that you asked, good that you told so that we could learn. Good. Now see the formula. Right? So this potential energy is nothing but, I just told, work done, right? So this is the work done against the cohesive forces. So what kind of forces are these? Instead of attractive, you can also write attractive cohesive forces. Attractive cohesive forces. So the work done against the attractive cohesive forces, right, is stored in the form of additional surface energy, right? Additional surface energy. And therefore we write delta U, or work done, or potential energy, right? Work done is nothing but delta U or delta W. So delta U is potential energy, right? And delta W is work done. What is it stored as? It is stored as potential energy, and its value is given by surface tension S into change of area. So this is change of area, or the increase in the surface of the liquid. This delta is increase in the surface of the liquid. Increase in liquid surface area. Increase in liquid surface area. Right? So on this basis, we define some of the formulas as one by one, right? Let's say we have work done in in blowing a liquid droplet. In blowing a liquid droplet. It's a liquid drop. Remember, liquid drop. That means inside it, outside it, there is water everywhere. Okay. So I'll represent it by a circle of this sort. Let's say a small drop, right? And we turned it into a larger drop by some process. By some process. Or we increased its surface area. That is the key. Right? Or I can also say, or we look about it more. So this is the concept right now, okay? That we had a small drop, we turned it into a larger drop. So Anukriti, can you tell me which one of the two should have larger surface area, smaller drop or the larger drop?
The larger drop.
Larger drop, right? Or very obvious. Let's say the surface area of the smaller drop is A1, surface area of the larger drop is A2, correct? Now the work done, just now we wrote down the formula as it is given as C. It's given as product of surface tension and change in area, right? So we have work
Yes.
done is S times of delta A. S times of delta A. What is
Delta
delta A? What was the surface area over here, Anukriti?
A1.
Let's say if I take R1 as radius here and R2 as radius here. So area will be pi R1.
R1 square.
What should be the area here? Pi
R2 square.
R2 square. Absolutely correct. Now, how will we define the work done in doing this work in making the liquid drop expand?
Surface tension into pi R1 R2 square minus pi R1 square.
Pi R1 square minus pi R2 square. Correct? So let's take pi common from that expression and we will have S into pi times of R2 square minus R1
minus
square.
R1
Right?
square.
Am I correct?
Yes, sir.
Easy to understand?
Yes, sir.
Please take this note. Please take this note. Everyone in the class, please take this note. Next one is, let's say now we are talking about a soap bubble. Work done in blowing a soap bubble. So soap bubble is something which we all have experimented with when we were little children, right? And we sometimes even keep doing this even now, right? What is so magical about it? See here, a soap bubble, tell me, has how many surfaces? So when I say a surface, remember surface means I am talking about that surface which is in touch with air, in touch with air. How many such surfaces are there? Um, Karuna, can you try? Let's say I talk about a liquid droplet. How many surfaces this liquid droplet has, Karuna?
So infinite.
No. Think again. At how many points? I'm not talking about the points. I'm talking about the surfaces. How many surfaces this liquid droplet has? So let's say this is the liquid which is filled in this layer. Okay. So it, in fact, it is not a droplet. Now I'm talking about a bubble. Pardon me. It's a bubble. It's a soap bubble. So here is that soap or that liquid solution which is filled here. Inside there is air, outside there is air. Now tell me how many surfaces are there which are in touch with air?
Two.
Two. Very clear, right? Very clear. So you have one surface over here which I am painting yellow. See this one. The other surface is over here. Am I correct?
Yes, sir.
You have two surfaces. So each one will have some surface energy.
Yes, sir.
Now I'm telling you a very beautiful fact. Listen to this very, very minutely or very focused in a focused pattern. See, this inner radius and this external radius are almost equal. Let's say I call them as R and R dash, R and R dash, right? So this R and R dash are almost equal. Why? Because this layer of soap film between them is very, very thin, is very, very thin. Because this layer is very thin, the radii are almost equal to each other. Radii of the inner surface and radii of the outer surface. Radii of the inner surface and radii of the outer surface. They are almost equal to each other. They are almost equal to each other. Why? Because the liquid droplet is, or because this liquid film between them is very, very thin, because there is thin liquid film between them. Is this point clear? Karuna,
Yes, sir. Yes, sir.
Anukriti,
Yes, sir.
Sheila, is this point clear? So thin liquid film, thin liquid film is there, is present between two surfaces, and that thin liquid film is causing the radii to be almost equal to each other. The radii to be almost equal to each other, right? So you have, in this case, work done is given as, again, S times of, right, change of surface area. Now suppose you again blow this into a bigger droplet. You suppose now blow this into a bigger droplet. So maybe you can draw it in this pattern, right? So let's say you make a bigger droplet out of it. Okay. Again, you have liquid film which is filled in between. On this entire zone, in this entire zone, there is liquid film. Right? And you have two surfaces, inner and outer. So one change of surface energy will be reflected for the outer surface, whereas other change of surface energy will be reflected from the inner surface. Am I correct, Mahila?
Yes, sir.
Right? So you have two surfaces and therefore you'll have two terms. One will be for inner surface and one will be for outer surface. But here is the key. Both the radii are almost equal to each other. Are almost equal to each other. Both are equal to each other. Therefore, all you have to do, write the same value. Write the same value. It was actually 4 pi r square. I'm sorry, not pi r square. This is not a circle, right? This is a sphere. So here you'll have a 4. Here you'll have a 4. This was clear, right, to everyone? Surface area of a sphere is 4 pi r square, right?
Yes, sir.
Anupati, Karuna, is it clear? Mahila,
Yes, yes, sir.
right? Okay. So now that we know that this surface area is 4 pi r square, right? So here what will be the surface area? 4 pi r square plus 4 pi r square. How much does it become? 8 pi r square, right? Am I
Yes,
correct?
sir.
And
Yes, sir.
rest things remain same. Change of surface area. Let's say here the radii was r1, then the radii became r2, right? And surface area changed from a1 to a2. So I can write s times of a2 minus a1. Let's say surface area was a1 here and then a2 here. So s times of delta a or a2 minus a1 is the work done in blowing the soap bubble. And in case of area, we are actually taking total area, that is for the inner surface and for the outer surface. See, mark the difference. Mark the difference. Here we are talking about a droplet. Inside and outside, difference is there. Here you have water on the inside, whereas here you have air on the inside. That is the key. That is the difference. Air is on the inside and air is on the outside. Whereas here you have water on the inside and air on the outside. Now, is it clear to everyone what is the difference between a bubble and a drop, right? And how do you actually relate work done with surface area in both cases? Karuna, is
Yes,
this
sir.
clear?
Yes, sir.
Okay. Similarly, let us take another example. Let's say we talk about drops, drops splitting. Let's say we talk about drops splitting. So we had a bigger drop or bigger soap bubble, right? Or bigger drop that split up into several droplets. So let's say I had a bigger drop, okay? Now the magic is when you split this drop no in different droplets, the magic is the surface area increases. The surface area increases rather than decreasing. When you have several droplets which are formed from a bigger droplet, its surface area increases. Tell me one thing. If its surface area is increased, then definitely surface energy has also increased, right? So if the surface area increases by this in this process, Mahila, tell me, if the surface area is increased in this process, then the surface energy has also increased, right? Am I correct? I think Mahila has not been able to be because in the connection because maybe network issues. Karuna, tell me, if the area has increased, that means definitely surface energy has increased, correct?
Yes, sir.
Now suppose that surface energy has come at the cost of energy from water. Energy from water. That means water also had some energy or not, because of the virtue of its temperature, right? Because of the virtue of its temperature. Correct? Correct?
Yes, sir.
So suppose
Yes,
that
sir.
energy has come because of the temperature of the liquid, and now that has turned into surface energy. Now that has turned into surface energy, then definitely there might have been a drop of temperature. There must be a drop of temperature, right or wrong? Correct?
Yes, sir.
So
Yes, sir.
drop of temperature of what? Of the droplet, of the droplet. So I am saying, if the internal energy, if the, take this note, if the internal energy of drop goes to or converts into surface energy, if the internal energy of the drop converts into surface energy, if the internal energy of the drop converts into surface energy, write it, if the internal energy of the drop converts into surface energy, written,
Yes, sir.
internal energy, suppose I denote it by IE, right? Then internal energy decreases, therefore temperatures of liquid, temperature of liquid will be less. Please write this down, class. Temperature of the liquid is lesser. Written,
Yes, sir.
Mahila, Anukriti, written.
Yes, sir.
Okay. Now let us move to the next part. Let us see the mathematical form of it. So we have a bigger droplet turning into smaller droplets, and let's say the radii will change, but the volume should remain same, right or wrong? The volume should remain same. Total volume will remain conserved, right? Total volume should remain conserved. Am I correct?
Yes, sir.
So
Sir.
let's say each one has a volume small v. Each one has a volume small v, whereas the larger liquid droplet had a volume capital V. Let's say the let's say all of these drops are actually identical in nature, right? We are assuming that all of these new drops are identical in nature. So we'll have generally 2 or 3 equations which will help you all in this expression. So first expression that should help you all is that volume remains same. So let's say there are n droplets. Let's say there are n droplets. So we'll have total volume is conserved. Therefore, total volume of one bigger droplet is equal to n times volume of each droplet. Correct? Right? And we know that capital V is 4 by 3 pi into capital R cube, and small v is equal to 4 by 3 pi small r cube. When you substitute it over here, you will get 4 by 3 pi cancelled on both sides, and therefore capital R is equal to n times of small r cube. R cube is equal to n into r cube, small r cube. Correct? Now, if you want to write capital R, it is basically n in n power 1 by 3 into r. And if you want to give what is the radius of each of the smaller droplet, that radius will be given as r into or r upon n power 1 by 3 or r into n power minus 1 by 3. Correct? Clear? How will be defined in this case the work done? So in this case the work done is S times of final area, final surface area minus initial surface area, right? Since we are talking about droplets, so it will be 4 pi, right? So S is equal to 4 pi and not 8 pi. 8 pi was the case of bubbles, right? So 4 pi into what should be the surface area here? Surface area of one droplet will be n times
R
of,
by
yeah. So this we are taking total surface area. So let's say each one has a surface area A. So I can take it as n times of A, correct? Minus of the surface area of the larger drop, right? Right? So we'll have S into 4 pi. What's the surface area of each droplet? 4 pi small r square, correct? So we can write that over here. This is n into 4 pi. 4 pi we have already written r square. Okay, I think we'll not write r over here. Sorry, 4 pi over here. So this will become 4 pi r square minus 4 pi r square minus 4 pi capital R square. And here with the small 4 pi r square, we'll use the n term. Why? Because this is basically 4 pi r square, right? This is the surface area of one droplet into n minus 4 pi capital R square. 4 pi capital R square. So this is how I am getting the work done. The work done. Correct? Is the concept clear? Formula clear?
yes,
Everyone?
sir.
Karuna?
Sir,
Anukriti? Okay, good. Now, just the opposite. Let's say you have drops coalescing into each other. Let's say you have drops coalescing or joining together. Then what should be the case? It will be, the formula will reverse, right? Let's say this was the case when one bigger droplet is splitting into many droplets, right? Now let's say several droplets are combining together. So combining of droplets is called coalescence. What is it called? Coalescence, right? So let's say they are coalescing into each other. Coalescence of drops to form a bigger drop. So in this case also this relation will remain the same, right? Between R and capital R and small r. Again we will have capital R is equal to n power 1 by 3 into small r, right? Where n is the number of droplets that have coalesced. Again you will have change in the potential energy, right? Is equal to S times of final minus initial, right? So you have capital A minus n times of small a. Therefore, you have S into 4 pi whole times of capital R square minus n into. Am I correct? Am I clear? Everyone, this is the work done here. Is the concept clear? Karuna? Anukriti?
Yes, sir.
yes, sir.
Now, one beautiful fact about it. In the last case, what had happened? The temperature of the liquid drops had gone down. The temperature of the liquid drops had gone down, right? Because the surface area had increased. Because the surface area had increased, therefore energy was converted from internal energy to surface energy, right? And therefore temperature, and that was at the cost of temperature. At the cost of temperature. What will happen now? Karuna, what should happen now? Here the
So
net
the
surface area
temperature
is
should
decreasing. Net surface area is decreasing. So now surface energy should convert into Which energy? Internal energy, right?
Yes, sir.
So since surface energy will convert into internal energy, now what should happen?
Temperature should
Increase,
increase.
right? Initially, in the initial case, in this case, it had decreased. Now it should increase. And what temperature are we talking about? This is the temperature of the liquid. Temperature of the liquid. And please mark, in all of these cases, that is coalescing of the droplets together or splitting of the droplets, we are assuming there is no heat exchange taking place between the liquid and the air. Liquid and the air. That means we are assuming that this is basically an adiabatic process. That is no heat exchange, no heat exchange with surroundings. Please remember this, with surroundings. And when do you take such a process? In thermodynamics, you have two concepts. One are called as fast processes and one are called as slow processes. So fast processes are generally adiabatic. So splitting is generally very abrupt. It's very fast. So we assume that it is a adiabatic process. And every adiabatic process will not allow, all the adiabatic processes do not allow the heat exchange. With the, here heat exchanges, we are talking about heat exchange with the surrounding, heat exchange with the surrounding. Are we clear with this, Karuna? Are we clear with this, Anukriti? That the process is adiabatic in nature, the process is adiabatic in nature, and therefore there is no heat exchange with the surroundings, and therefore I also call the processes very fast, or vice versa. In thermodynamics, sometimes you will not be given whether the process is isothermal or adiabatic. They might simply tell you that the process is slow or the process is fast. Please take a note of this also if you haven't already, that whenever a process is slow in thermodynamics, see, all the chapters are interlinked, right? So in thermodynamics, we see that if the process is slow, then we take this as isothermal. Why do we take it as isothermal? Because when the process is slow, there is sufficient time of heat exchange. A slow process allows sufficient time for heat exchange, as sufficient as there is sufficient time for heat exchange. As there is sufficient time for heat exchange, and these are fast processes. Fast processes are adiabatic. Why? Why are they adiabatic? Because there is no sufficient time for heat exchange. As there is no time for heat exchange. No time for heat exchange. As there is no time for heat exchange. Are we clear with this?
Sir, I have a doubt.
Yeah, tell me.
The previous concept.
Yes.
So when the bubbles, the droplet splits,
This one, this case,
that
right?
time,
That time,
yeah,
yeah,
that time the surface area increases,
that time the
right?
surface area increases. Absolutely, yes.
Uh, and in the second case, when they are combining, the surface area decreases.
Right, yes.
So the net surface energy in the second case will be negative, sir.
It will be negative. Yes, it will be negative. So what does negative mean? That surface energy will now go into increasing the temperature. So basically this is happening. Whenever coalescence or whenever, so you can say, whenever coalescence or splitting is taking place, I'll maybe write a summary chart here. Whenever there is a splitting or coalescence taking place, whenever there is a splitting or coalescence taking place, there is actually an interchange of energy happening in the liquid. Interchange of energy happening. So in case of splitting, when one droplet has splitted into several droplets, I can clearly see that there is an increase in the surface area. As there is increase in the surface area, the surface energy increases. As the surface energy increases, I'll write it better. So wait a minute. So as there is an increase in the surface area, this leads to an increase in the surface energy, right? So on account of what will this surface energy increase? See, the both the processes are adiabatic in nature, right? Both the processes are adiabatic in nature. Since they are adiabatic, they are not allowed to take or give heat to the air outside. Am I correct, Karuna?
Yes, sir.
Adiabatic means no heat exchange with the air, no heat exchange with the air, like with the surrounding air there cannot be any heat exchange. What does this mean? Since the since the surface energy is increasing in first case, surface energy is increasing in first case, then the internal energy of the molecule will decrease, or that droplet, those droplets or that of the liquid, internal energy of the liquid will decrease, and therefore this will lead to decrease of the temperature of the liquid. Just the reverse happens in the second case. Here the droplets are coming closer together and forming a larger drop. As they form a larger drop, there is actually a decrease in the surface area that is taking place. A decrease in the surface area that is taking place. That decrease in the surface area is causing a decrease in the surface energy. That is why delta S, or change of surface energy, the delta SE or change of surface energy is negative. Correct. Change of surface energy is negative. So a negative change means the surface energy has decreased. The surface energy has decreased. So when the surface energy has decreased, where does it go? It goes into the internal part of the liquid, where it goes into rising of the temperature, right? And therefore internal energy increases, and so you can say that temperature of the liquid increases. You can remember this by trick, that surface energy plus internal energy, sum of these two is constant. This can be a trick which you can keep in mind. So sum of surface energy and internal energy is constant. Sum of surface energy and internal energy is constant. If one of them increases, the other decreases. If one decreases, the other increases. If like in this case, surface energy was increasing, so internal energy was decreasing. In the second case, as the surface energy is decreasing, the internal energy is increasing. Please take this note with you. Yes, Karuna, ask your doubt.
Clear, sir. Yeah.
Is it clear? Okay, great. Yeah, great. So this is how we have understood the concept of potential energy. Then we have understood the concept of surface energy and its formula, how we understand the work done in case of a liquid droplet, in case of a soap bubble. We've also seen about the interconversion of surface energy and internal energy in case of splitting and coalescence. In case of splitting and coalescence, right? Clear? Anukriti, is the concept, whatever we have read in class, is everything crystal clear in mind?
Yes, sir.
Okay. Now, let's do one thing. Let's take a short break of 5 minutes. let's resume after that, because I would like both of you to finish off the three simple topics we'll be taking up: angle of contact, capillary rise, and excess pressure. See, we are done with two already in the five topics that we had to cover, right? We're done with two, three more to go. So let's take a break, right? A short break of 5 minutes, and let's resume in 5 minutes, right? And as we resume, we'll continue from here. Am I clear? Right? Okay. Uh, so in case you could hear my voice, can you just respond? Anukriti, Karuna?
Yes, sir.
All right, all right. Great.
Yes, sir.
Right, right. We'll just resume, okay? So welcome back, class. Let's start off. We are talking about angle of contact now. Angle of contact is basically the angle between liquid and the vessel. Liquid surface, angle between liquid surface and the vessel. Right? Angle between liquid surface and vessel is called as angle of contact. So there are generally two types of angles which are found. One is acute, the other is obtuse. So when you see the surface of water and mercury, they will differ in this pattern. So let's say we have water, it might look something like this. Let's say we have mercury, it might look something like this. One is called as a concave surface, one is called as the convex surface. So from here if you look, this will be called as concave, whereas this one will be called as convex. Concave and convex, right? And you have next part is, let's see the angle of contact. Okay, so just see here. Okay, I'm drawing one vector here and the other vector in this direction. So now you'll be very clearly seeing that this is the angle of contact which I'll just draw, this one. Whereas in case of mercury, so this one is water. Here the angle of contact, as you can see, is acute. Whereas when you talk about mercury, right, see how I'm drawing the angle of contact. This way. This angle is obtuse, right? This angle is obtuse. So we have two types of angles, right? Acute and obtuse. And we have also understood that how are the shapes of the surfaces. These surfaces are sometimes also called as meniscus. Each surface is called as meniscus. Okay, so this is called as a convex meniscus, whereas this one is called as a concave meniscus. Correct? So this is what the term is about, right? If the concept is clear, we'll take the next part, which is called as the concept of excess pressure. So the concept of excess pressure, we are seeing that whenever there is a free liquid surface film, right? A free liquid surface film, then on the two sides of it, there will be a pressure difference. There will be a pressure difference if this film is not plane. So what I mean to say is, let's say I have a surface of soap bubble, which is something like this. Let's say if it is a plane surface, Pressure here is P1, pressure here is P2, vapor pressure. Let's say vapor pressure on the two sides is P1 and P2. Then those P1 and P2 will be equal when in case of a plane surface. But if the surface is not plane and this film is in the form of a sphere, this is in the form of a sphere, right? Now we can talk about again three cases. Again three cases. But first let's talk about one by one. Yeah, three cases. So each one of them. Okay, let's talk about each one of them one by one, right? So the first case, this one is that of a liquid droplet. It's that of a liquid droplet. So this is a liquid drop. This liquid droplet has a difference of pressure. Always remember, now have this understanding. I'm with my hand, I'm making a bulged surface, right? Let's say I'm making a bulged surface this way. Always on the outside of the bulged surface and the inside of the bulge surface, when you talk about the pressure, so pressure here on the inside is always more. Pressure on the concave, from here, this will be called as convex surface. This is called as concave surface, okay? So for the concave surface, the pressure is always higher. I will repeat, for the concave surface, pressure is always higher. So you will see that in this figure, if I talk about two surfaces or two areas, let's say the inner area and the outer area. So which area should have a higher pressure? Inner, right? Because here there is a concave side. See, this one is concave. This part is concave, right? Where from here, this part is convex. So concave pressure is always more than the convex pressure. This is a trick. You can write this with you, that always concave side has a larger pressure than the convex side. The example which I gave you just now. Now you will have P2 is greater than P1 by how much amount? By this amount. 2s by r. 2s by r. Where what is S? S is surface tension, whereas R is the radius of this liquid droplet. R is the radius of the liquid droplet. Now take the same thing, right, for a air bubble. Now this is an air bubble. This one. This one is next. This one, the one which I'm drawing, third one, is the air bubble. This is air, and where is it? Inside water or any liquid, okay? Air bubble. Let's say inside the sea, there are several bubbles coming up, right? So this is the air bubble, okay? And here the excess pressure on the inside, let's say this is P2 and here the pressure is P1. So again, P2 minus P1 for an air bubble inside a liquid, this difference of pressure is called as excess pressure, and its value is given by again 2s by r, where what is r? R is this radius, right? Now take the case of a soap bubble. Case of a soap bubble. Now, in case of a soap bubble, you have this expression. P2 minus P1. Karuna, quickly tell me, there are two surfaces. So instead of 2s, what should I write? What should I write?
4s.
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 Right? Because there are two surfaces, right? This is one surface. More than surface, I should say interface between air and water, right? That is how a surface is formed. So here we had two surfaces again. So therefore you have the formula for excess pressure will be given by, in case of a liquid drop, as 2s by r. Here the excess pressure or the difference of pressure, you can also call this as difference of pressure on the inside and the outside part. Difference of pressure on the inside and outside part, correct, is called as excess pressure. Now we learned that its value is 2s by r for a liquid droplet. For an air bubble it is also again 2s by r, and for a soap bubble it was 4s by r. Let's see one last concept, which is the concept of capillarity. Very beautiful and interesting at the same time. The people from the biology background will know that the water in the sap of a plant, I think, or maybe the sap liquid inside a plant, that is transported via capillary action. That is transported via capillary action. So it is basically capillarity is the rise and fall of liquid in a capillary tube, right, with respect to the surrounding liquid. So capillarity, right, capillarity or capillary rise, capillarity is basically rise and fall of a liquid, rise and fall of a liquid rise and fall of a liquid inside a capillary tube, inside a capillary tube with respect to surrounding liquid, with respect to surrounding liquid, is called as capillarity, right, is called as capillarity. So let's say we have a capillary tube, okay, which is present in, I'm making this very, very large, although capillary tubes are actually very thin, very, very thin, right? So I've made a very huge diameter just for the sake of representation. Let's say I've filled a water. Let's say I've filled some water in this liquid, in this vessel. So you will see that water will start rising and will come and halt at some height. Water will start rising, it will start rising and it will come and halt at some height, right? So that height at which the water will halt, right, is given by 2s cos theta by r rho g. 2s cos theta by r rho g. R rho g. What is r? What is rho? What is g? So this r is the radius of the tube. Small r is the radius of the tube or the capillary tube, right? This h is the height up to which this water has risen, or that liquid has risen. Not only water, any liquid. This h is that height up to which that liquid has risen. This theta is the angle of contact between this surface theta is this angle of contact between the surface and the liquid surface and the vessel. This is theta. And of course, S we know is surface tension. Rho is the density of liquid. Rho is the density of liquid. So this is how you give this height. You should very well mark that how H is depending upon rho R. Sometimes you have questions. Let's say here H is directly proportional to S, right, cos theta upon S cos theta upon rho, right? When I talk about liquid property. So for every liquid, surface tension may be different, right? For every liquid and some other surface, angle of contact may be different. Similarly, density of liquids may be different. So you may be given two cases and you might be asked to find out the ratio of heights up to which the liquids will rise when put in a capillary tube, right? So such kind of questions sometimes are asked, right? Or sometimes you might be asked to draw a graph. Sometimes you might be asked to draw a graph between what? Between H and R. So how will you draw that graph? From this figure, it's from this formula, it's clear that H is inversely proportional to R. And any two quantities which are inversely proportional, the graph between them is a rectangular hyperbola, something like this, right? So this is also a keynote point, right? So these are some key things that you should understand, right? This is something called as Jurin's law or Jurin law, right? And what else? I think these are few things that you should know, you should remember, right? Sometimes in the question you might not be given R, rather you might be given radius of the meniscus, capital R. Radius of the meniscus. So radius of the meniscus or capital R is basically small r upon cos theta. Where what is small r? This small r is the radius of the capillary tube. Right? So these are some concepts that you all should know, correct? These are some concepts that you all should know. Now, I think one more important last concept which I will want to tell you both or tell you all who are in this class is that, have a look. Suppose I turn the tube. Suppose I turn the tube, okay? So say I have, this was the vessel, right? In the chapter fluid mechanics, before that we have something called as hydrostatics, where we read that the height or the pressure at the same height remains the same, right? I hope you all have also read it, right? Pascal's law. So suppose initially my vessel was this way, or my mercury, or I'll say the capillary tube, to be very important, to be very precise. Let's say this was my orientation of the capillary. This capillary was oriented vertically. The capillary was oriented vertically. So what will happen? Because the vertical orientation of the capillary, right? Because the vertical orientation of the capillary, here is how the height of the liquid will look like, H. Let's say I have tilted it by angle, alpha, okay? Alpha with the vertical. This angle is alpha with the vertical. Then also the height will remain the same. The height will remain the same height. But it's very important now that what will be the length of water which will be present here. The length of water will be this, L. Now see, I'm drawing a triangle, or the other way around. This is L, this is H, right? Whereas this angle is theta. So I can have, or sorry, alpha, the rotation, the angle by which the object has been tilted. So I have this is alpha, this is also alpha, this is H, whereas this is L. Now we have cos alpha is equal to base by hypotenuse, right? So I can write the length of the liquid, length of liquid in the capillary. So this is case when tube is tilted. Tube is tilted by angle alpha. When the tube is tilted by angle alpha, then the length of liquid in tube is equal to h by cos alpha. L is equal to h by cos alpha. So please take this down. This is the last formula in this entire chapter which I wanted to introduce all of you. H is equal to L by cos alpha. So in today's class, we understood the concept of surface tension, surface energy, excess pressure, and capillarity one by one, right? If there are any doubts, let me know. Yes. Karuna, any queries?
No, sir.
Okay. Anukriti, any doubts, any queries you would want to ask?
No, sir.
Clear everything?
Yes, sir.
Okay. Until now, because we have done everything based on the formulas, it's superbly important that you once or twice read these formulas and practice them, perhaps jot them down in your formula copies, right? And we'll accordingly solve the questions in the coming classes, right? So thank you everyone for being in the session. Thanks a lot. Let's join tomorrow and continue with the practice, after which we'll start electrostatics as our next chapter of class 12, right? In this revision series. Thank you everyone. Thanks a lot.
Thank you, sir.